Thank you so much, everybody. We're going to go ahead and get started. My name is Gabriel Cardona, and I am a developer evangelist from Ava Labs. I am on the developer relations squad. We are led by the amazing Luigi Di Meo, who is here at the conference. The team recently grew quite a bit. It now consists of Usman Asim, who is here, Martin Eckhart is here, Megan Fitzgerald, who unfortunately did not get to make it, Andrea Vargas, who recently joined us last week, very stoked to have her on the team, and myself. And our goal is basically to accelerate the adoption of Avalanche by developers, and we hope to provide resources which enable developers to go from idea to application and to transition from being a hobbyist or an amateur into being a professional. And we are always hiring. Go check out avalabs.org/careers if anything you see at this conference excites you. We're not just hiring on the DevRel squad, we're hiring across the entire team. So if something you see at this conference interests you and you think you can add something to our team, go check out avalabs.org/careers. This workshop, is going to be building a simple Web3 game. We're going to talk about the convergence of Web3 and gaming, and then we're just going to basically build a very simple Web3 game to kind of demonstrate the potential of the convergence of Web3 and gaming. So before we do that, let's just take a glance at traditional gaming. So gaming is now the world's most popular form of entertainment. The entire industry and sector is now worth greater than $200 billion, and it's growing at over 10% year over year. And we expect by the end of this year, by the end of 2023, there will be over 3 billion gamers in the world out of a population of around 8 billion. So we're right now hitting an inflection point where soon nearly half of the people alive on the planet will identify as a gamer in some form. And within our lifetimes, nearly everybody on the planet will identify as a gamer. So it's an absolutely huge opportunity to have an impact on most of the human condition. Gaming currently spans dozens of genres, but there are really three major platforms, both online and offline. So we have PC, we have mobile, and we have console. And when it comes to monetization, there are really two main models. So we have premium games, and these charge a fixed price for full access. So you can think about like Super Mario Brothers, for example, where you pay maybe $50 or something like that, and you get access to the full game. And then there's also free to play. So these games seek to attract a very large player base, and then they gain profit by in-game purchases and advertisements. So think about something like Fortnite, for example, where you can get the basic user experience, and they'll give you some default skins, but there's always some type of social pressure. For example, I hear my son and his friends call people defaults, basically, who are using the free skins that you get when you start. And there's also some type of social pressure to, purchase more skins via in-game purchases, and then there's also advertisements and events and etc. But as the entire gaming sector grows, as we go, we cross this 3 billion threshold, and as we get into, most of the humans on Earth identifying as a gamer, the setbacks are much more evident. So there's really a strain on consumer spending. All of the purchased assets only hold value within the ecosystem of that particular game. And even in that context, gamers don't really own anything. So they don't own their in-game assets, they don't own their personal data. The game publishers are really calling all the shots. And I often point this out to my son. I myself have spent a non-trivial amount of money across Fortnite and Call of Duty and Pokemon Go, all these different games for him. But at any moment, in theory, he could be deplatformed by one of these games, and he would basically lose access to all of the time and money that we've spent, or he and I both spent on this game. And so Web3 gaming really facilitates a huge power shift from creators to players. So what is Web3? I suspect we don't need to spend too much time on this slide. Everybody in this room knows this, but we'll briefly discover this so we're all on the same page. Of course, the very first Web 1.0 was created by Sir Tim Berners-Lee in 1989, and we consider the Web 1 era from about 1990 to, let's say, 2004, 2005. And of course, Tim Berners' original vision was to create, a decentralized protocol that allowed information sharing from anywhere in the world. And the main highlights of the Web 1 era was that it was really static documents. There was very, very limited interactivity between users, and there really wasn't any user-generated content. Around 2004, 2005, we see the emergence of AJAX, asynchronous JavaScript, and XML. We see the whispers of the beginning of modern CSS, modern HTML, modern ECMAScript, and JavaScript. And we see the emergence of social media platforms, and the web sort of shifted from being read-only to these companies providing platforms for users to interact with each other and to share user-generated content. content. And so then the web exploded, but as more and more people came online, a handful of top companies began to control a disproportionate amount of traffic and the value generated on the web. And so Web 2.0 really gave birth to the advertising-driven revenue model. And though users can create and contribute content, they don't really own it, and nor do they benefit from its monetization. So Web 3, what we're all here celebrating together today, is really this catch-all term for this vision of this new decentralized censorship-resistant internet. It's better. And at its core, it uses blockchain technology, cryptocurrencies, and NFTs to give power back to the users in the form of ownership. And I saw somebody in 2020 say it best on Twitter. Web 1.0 was read-only. Web 2.0 is read-write. Web 3 is read-write and own. So to summarize, Web 3 is decentralized. It's permissionless. It has native payments in the form of cryptocurrencies and non-fungible tokens. And Web 3 is trustless. So how about Web3 gaming? Again, Web3 games are different from traditional games in that they allow players to earn cryptocurrency and non-fungible tokens, both powered by blockchain technology, and players can then own their acquired asset, which can then be traded on marketplaces for virtual or real-world currencies. And on the right, you can see this really great slide. I'll give you a second to kind of go over that. But again, as I mentioned previously, Web3 gaming really just facilitates a huge power shift from creators to players, and it is very much here to stay. We're really just in we're in the very beginning of this paradigm. And as I mentioned, we're about to cross 3 billion gamers by the end of this year. Within our lifetime, nearly everybody on the planet will identify as a gamer, and this is just such a huge opportunity to have an impact on humans all across the world. Okay, so I have this demo. Let me exit these slides here. We're going to be basically building this little game I'm calling Run. I want to give credit to the gentlemen at Dapp University. They originally created this repo. If you check out their YouTube channel, Dapp University, it's a great place to learn about Web3 technology and a bunch of tutorials. I forked it and made some changes, so this isn't exactly what's on their website, but in the spirit of open source, I do want to give those gentlemen credit because there's a really, really great channel. So Dapp University, go check it out on YouTube. Basically, the game we're going to build right now has the same mechanics as the little dinosaur game that shows up in your Chrome browser when you don't have a network connection. So basically, we're going to have a little icon of a guy. He's going to be running from left to right on the screen, and off of the screen on the right, we're going to have obstacles and NFTs which enter the screen. I'm going to press the spacebar to jump and avoid the obstacles. There are 2 different reward mechanisms. So there's going to be a run token. This is an ERC20 token, and the longer we stay alive, we'll just be rewarded run tokens. And then second, as I mentioned, there's going to be NFT icons which come from the right side of the screen. I'm going to try and jump and grab them. The more that we jump and collect, the more we'll be rewarded at the end. These NFTs are visible in OpenSea's Fuji NFT marketplace. So if anybody wants to play along with this later at home, you can check out my GitHub repo here at github.com/cgcardona/run. I gave this same demo in ETH Denver about a month and a half ago, and it was an hour versus a half an hour here, and I actually did code everything from scratch, and I spent the last 10 minutes or so trying to debug everything, and I finally got it to work, and that was a little bit stressful, and since this is half an hour and I have less time, everything is working here. I'm going to go over the code, but I'm not going to make any changes because I'm positive everything is going to work. The only reason I mentioned that is because I'm running a local 5-node network on my machine here, and I'm going to deploy the smart contract to that. So we will not be able to see these NFTs in the OpenSea marketplace, but as I mentioned, if you clone this repo, all of the steps are here for installing the dependencies, compiling and deploying the smart contracts, and then you yourself can go check this out on the OpenSea marketplace. So this is a really great repo to build off of if this kind of interests you. So let's talk about the tech stack we're going to be using. We're going to be using a combination of Web 2 and Web 3 tech. So of course, we're going to have HTML for the structure of the web page or the app. We're going to be using CSS for styling it. We're going to be using JavaScript for adding interactivity. Next, we're going to use Solidity for writing the smart contracts. As I mentioned, we're going to have 2 different smart contracts. The first is an ERC20 fungible token with a ticker symbol run. And then, as I mentioned, this will be what you're rewarded for the longer you stay alive before you hit an obstacle. And the second is an ERC 1155 token collection. So if you know about ERC 20, you know this is a fungible token. There's ERC 721, which is non-fungible tokens, and then there's ERC 1155, which are fungible agnostic token collections. They can be either fungible or non-fungible. In the case of this demo, we're going to be making a non-fungible token out of the ERC 1155 token contract. Next, we're going to need Node.js and NPM to install and build all of the dependencies. We're using Hardhat as our Web3 development environment. So this contains all of the tools you need to develop and debug and test and deploy your smart contracts. We're also going to be using Ethers.js to interact with the blockchain. This will be used for the app to talk to smart contracts, to issue the tokens, and then to basically claim them to the core wallet, which will be the very last step we do. And then lastly, we're using the live server extension to launch a local development environment and run the app in the browser. So let's dig in. Okay, perfect. Okay, wonderful. So this is our index.html file. Before I point this out, I guess I should point out over here on the left, we're going to have two directories. We have contracts and game. The games is going to host the Web2 assets, and the contract will host the Web3 assets. So in the game directory, first we'll open this index.html file. It has everything you would expect to see in an index.html file. Before I kind of go through this, you can see at the bottom, for example, we have script tags where we're including dependencies from a CDN, and this is an index.html file. You could refactor this into like a React app or an Angular app, and you could pull these dependencies into a package.json file. You could definitely clean this up. The reason that we didn't do that is simply it adds another level of understanding, and I wanted to boil this down to its very essence so that people could follow along. But you could definitely clean this up and make it a bit modern. It's very rare, at least in my development experience on the front end, to kind of hard code scripts like this anymore. But just so if you're seeing that and you're thinking it looks a bit dated, that's the reason. We kind of wanted to abstract as much complexity away as possible and just boil it down to its very essence so that people are able to follow along. But you can see here we have everything you would expect. So we have the HTML5 doc type at the top. We have our title. We have a link which is pointing out to our style CSS file. We have this script tag, which is of type module. This allows us to basically reference these data-HTML5 custom attributes within the script tag. So that's what's happening there. Within the body, there are going to be 3 buttons at the top of the screen. Whenever I load this at the end, you'll see we're going to be able to claim NFTs, claim our run tokens, and connect the wallet. This will connect to MetaMask, but as I mentioned, we're going to be demoing this in core since this is, of course, an Avalanche Summit. All 3 of these contain this on-click event attribute, and then these claim NFT, claim tokens, and claim connect wallet respective functions, which we will implement here in a second. Then there's also going to be sort of 2 ways we keep score. So there is the score of the current game you're playing, and then there is a cumulative score. So you can see it says NFT score 0, run score 0. When we start playing, these will increment, and then whenever we hit an obstacle and we end our turn, they'll reset to 0, and those scores will get added to the cumulative total score. And then at the end, whenever we click the claim token and claim NFT buttons, these will get claimed to our wallets, and the whole score will get reset to 0. We have this game div, and inside of it we have this start screen div, which basically just says press any key to start. Whenever we press that, that'll get removed from the DOM by JavaScript. I want to really quickly show you the image assets that we have going. So we have this ground ping. This is going to be used to basically scroll from right to left to make it appear that the user is running across the screen. We have this NFT icon. I'm just using the Avox icon. As I mentioned, this will show up as an NFT on the OpenSea marketplace if you deploy this to Fuji or our mainnet. We have our obstacle ping. So this is what's going to be coming from off to the side of the screen that we're going to need to jump and avoid. If we run into it, that'll end our turn. We have the player jumps image. I don't know if you can barely see it there, but this is basically a ping that shows a kind of like a little stick figure jumping. We have player 0. I don't know if you can see these at all. We have player 0 and player 1. We're going to toggle back and forth between these to make it look like the user is running across the screen. And then we have our player stands, which just shows a stick figure standing there. This is the beginning state of the game. And then if we go back to the DOM, to the index.html file, here in the images, you can see that we have 2 different ground. Hold on one second. Here it is. Here we have 2 different images that are using the ground.ping. And the reason is we're going to be using JavaScript to basically move them from right to left, and as one goes off the screen, we'll have the other appear on the screen and then continue. So we're going to be looping back and forth between them to make it appear that the ground is moving and that the user is running. And then also we have the player stands. As I mentioned, this is the beginning state of the game, so it'll just show the user standing there until we press the space button and kick it all off. As I mentioned, we're using ethers.js, and here we have it just hard-coded out to a CDN. You could, of course, abstract this away and include this dependency via a package.json using Node.js. And then lastly, we have our blockchain.js script, which we're also going to implement. And then this is the script that allows us to connect to the wallet, to issue the NFTs, to issue the run tokens, and then to claim them to our wallet. So let's look at what's going on inside of our script.js file. So at the top, you can see we have 4 scripts here: ground.js, player.js, obstacle.js, and NFT.js. And I'm importing functions from each of those. We're going to implement those here in 1 second. We have some constants at the very top of this, which is the game width, which is how long the running track will be. And then we have the game height, which of course is the height of the game. We also have the speed scale increase. So basically this is the longer you play, the more challenging the game will get because it will increase. Here we have references to DOM elements. So sometimes you hear Web2 developers talk about DOM, the document object model. What is that? The document object model is an in-memory representation of your HTML document. So you saw we had that index HTML document. It's just a script, or it's just text. The document object model is an in-memory representation of that as nodes and objects that scripting languages can traverse. So when you have document.getElementById or document.querySelectorAll or document.querySelector, this is a DOM API. This is where browser and JavaScript kind of meet. So this isn't, document is not a JavaScript object. This is an object which is provided by the browser. And this allows us to basically traverse this object structure, get access to these different elements, and then either change them, update their properties, change the text, something like that. So that's what's going on here. Next, we have our set pixel. Where's it at? It's at the bottom. Here it is. We have our set pixel to game scale definition. So we want to make our game responsive, and for that we have this function which will give which will scale our game based on the screen size. Next, we have our update function. So in every game, you need some type of game loop. And in our game, it's going to be this update function. And here you can see we call this window.request animation frame. We call it here on line 29 and again here on line 45. And so basically, this window.request animation frame gets called whenever we can render content on the screen. And so here you can see we pass in the update function. So we have an update function, we're calling this method, and we're calling it recursively and passing it back in. And basically this allows us to create a loop. And inside the update function, we want to update our player on each frame, and we calculate this via this last time variable. So the first time we use it, it will be null. It's set up here to nothing, so it's a null, and you can see we check if it's null here on line 27. And we want to set the last time variable to the time it took, and then call request animation frame again, and then exit out of the function. And we calculate the time between frames using this delta variable right here on line 33. We only want to update our ground, player, obstacle, and other things on each frame. So we'll create these update functions. If you remember at the top of the screen, I imported them from files. We have to implement them. And then each time the update function gets called, we want to check if we've lost. And if we have, we call handle lose, and we reset all of the variables. Next, we have our check lose function. It checks if there is a collision with the player, and it uses this isCollision function below, which we are going to implement here. This isCollision function takes 2 rectangles and checks if there's been a collision between them. Below that, we've got our check if we got NFT method. And in a similar way, we want to check if we've got an NFT. So inside, we want to get the player rect, and we use isCollision. And if there's a collision, we want to remove the NFT from the DOM and increment the score by 1 and update the UI. We have our update speed scale. This function takes in the delta and updates the speed scale by adding it to delta times the speed scale increase constant, which you can see here. Next, we have our update score function. This also takes in a delta and adds it to the delta plus 0.01. You see this on this line right here. This is our current run score, and we basically want to make sure it's a whole number by using math.floor, and then we're basically updating the DOM using string interpolation right here. That's what's going on there. And then we have our handle start function. This is where we call all of the setup functions for ground, player, obstacle, and NFT. We reset the score and other variables, and we also want to hide the press any key to start, and then we'll call request animation frame to kick off the game loop. Next, we have our handle lose function. We have a couple window properties there that are available across all of the scripts. Then we have our handle lose function. Here we just want to add the current score we have after we lose our game, update the UI, and reset the scores to 0. And then after 100 milliseconds, which you can see right here on this set timeout, we want to listen again for events so that if we click a button, we're ready to play again. So after a 1/10 of a second after you lose, you can start playing again. Next, we want to check out this update custom property.js file. These functions are for taking in CSS on an element and updating it using JavaScript. So here you can see we have this get custom property. This gets a property from an element and returns it in JavaScript. We have set custom property. This sets the property on an element using JavaScript. And then we have increment custom property, which increments a property on an element using JavaScript. Next, let's check out ground.js. So again, at the top, we're importing the get, set, and increment custom property functions, which we just implemented in the previous file. We also have this speed constant, which is the speed at which the ground will move. Next, we get the ground DOM elements, and we have our setup ground function. So remember, there were 2 different ground images. The first will have a left of 0, and the second will have a left of 300, because if you remember, that's how wide the game was. Next, we have our update ground function, which is called in script.js. Inside here, we're going to loop over both of the grounds and increment the custom properties so that moves. And you can see we're multiplying by -1 here on line 17 because it's moving backwards. So it's entering the screen from the right and it's exiting the screen on the left. And once the first one goes off the screen, we want to update the second one. And if it's a -300, then we add a 600. And so this, as I mentioned, will loop between the 2 of them and will give the appearance that the ground is moving back and forth on the screen, or moving from right to left on the screen, I should say. Next, we have player.js. Again, at the top, we're importing the get, set, and custom increment custom properties from the update custom property.js, which we implemented. We also have these constants. We have the speed and the gravity, so you can tweak these however you want, to make the guy jump higher, make gravity more intense. Your call on that one. And then also we have the player frame count. You can see that it's 2 because if you remember, there were 2 images which we're going to bounce back and forth between to make it look like the user is running across the screen. Next, we have our setup player function. Again, we're using set custom property to set the bottom to 0, and we add an event listener for key down. This will cause the player to jump whenever you press the space key. And we have our update player function. Where's it at? Right here. This takes in a delta and a speed scale and handles the run and the jump. We have the get player rect, which returns the dimensions of our player. We're using this for is collision. We have set player lose. This sets the player to the losing state. So you'll see whenever I run into an obstacle, we set the player into the losing state. We have handle run here. This is the handle function that we're calling whenever we update our player. And here we want to check if the player is jumping. And if so, we add the jumping image. And here we also toggle between the 2 main images to make it look like the player is running back and forth. Here you can see we're doing that here with string interpolation, player element.source. And then we're using string interpolation, so it'll either be 0 or 1, and then we'll toggle back and forth to make the player look like it's running. Next, we have our handle jump. If the person isn't jumping, then we exit out of the function. If they are jumping, then we increment their bottom property. And then lastly, we have our on jump. And this checks if we've hit space and if the player is jumping. And if so, we exit so that we don't jump again. And if we're jumping, then we update these properties. Next, let's talk about obstacle.js. So again, at the top, import the get, set, and increment custom property functions, which we implemented. We have our constants here at the top. We have reference to the obstacle DOM element here. Next, we have our setup obstacle. Here we create an obstacle with the minimum spawn time, and at the same time, we remove all of the other obstacles. Here we have our update obstacle function, and this is called from within the game loop. So we query all the obstacles, and if they have a left property that is less than 100, then we remove them because that means they're off the screen and the player no longer sees them. And then we check if the next obstacle time is less than 0, and if so, we create a new obstacle. And we calculate the obstacle time by using this random number between function, which we implement at the bottom. We have the get obstacle rex, which returns the dimensions of our obstacle. We also have our create obstacle function. Here we're creating an image DOM element, so document.create element image. We're then setting, this is a HTML5 custom data attribute, so this would be data-obstacle equals true. That's what data set is. Then we're setting the source element to the obstacle ping, which I showed you in the beginning. And then we check if the, hold on one second. Yeah, we set the image source, and then we add it to the DOM. And then we have this random number between. This creates a random number which is used for spacing new obstacles. So in order to add a little bit of challenge to the game, we don't want each obstacle to enter the screen sort of uniformly spaced. We want to kind of make them randomly closer or farther from each other, which will make it a little bit more challenging to jump and to avoid. And then next we have our NFT.js file. This is actually nearly identical to the previous obstacle.js file. As I mentioned, we'll have obstacles and we'll have NFTs entering from the right of the screen. And in both cases, we want them to be randomly spaced to make it more challenging to avoid the obstacles and to join to actually jump up and hit the NFTs. So if you compare this NFT.js to obstacle.js, they're nearly identical. I just swapped out all of the references for obstacles with NFT. So this includes DOM elements and CSS and the image as well. And so next we want to check out our blockchain.js script. So at the top we have this connect wallet function. This will connect to MetaMask as well, but as I mentioned, since this is an Avalanche conference and Core is the official wallet of the Avalanche ecosystem, we're going to be using Core, but as I mentioned, this will work with MetaMask as well. We have this claim tokens function, which allows us to claim the ERC20 tokens to our Core wallet. And we have the claim NFT function, which allows us to claim the NFTs to our address, which would then show up in an OpenSea marketplace, for example. We're going to be coming back to this script in a minute because there's 2 contract addresses here, which we need to hard code after we compile our smart contracts and deploy them to our local network. So we'll see this again in 1 second. Of course, we have our style CSS script, our styles.css, and that's pretty much all of the Web2 components. So now if we jump on over to the contracts directory, this was actually created with Hardhat. So you can run npx hardhat new, and it'll create this directory structure for you. It'll give you a contracts directory, a scripts directory, a Hardhat config. Some things to notice in this Hardhat config: there are 3 networks which we can deploy to. So we have localhost, obviously, which is where we're deploying. We have Fuji, and then we also have mainnet. All of this works, of course. Some things to note here are over here I have this m-example. And then you can see we have a .env file here, which is grayed out. So basically what happens is you can resave this file as .env and then add .env to your .gitignore so that you don't accidentally commit it to GitHub. And then you can actually save a private key in this .env file. Again, you want to make sure that you add your .env to your .gitignore because you do not want to push an env to GitHub. There are people out there who have scripts who just watch GitHub over the their REST API, and they will look for .env files, and they'll scrape out secrets and immediately steal your tokens. So absolutely never commit any private keys to a GitHub repo. But that's what's happening here. So basically, in this .env file, I have stored 2 private keys, which allow me to sign the transactions for this. Next, we want to look at our contracts. So we have this run token. We're using OpenZeppelin contracts. So OpenZeppelin is, of course, like the industry standard for EMV smart contracts, which have been security audited and battle hardened, if you will. This is an ERC20 token. So this basically extends this smart contract. And then you can see we're overriding the constructor function and passing in 2 arguments. The first is the name of the token. The second is the ticker symbol, RUN. And then we have this mint tokens function, which is going to be called whenever we want to mint the tokens and call them to our wallet. And then we have these scripts to basically deploy it. As I mentioned, this will show the address, and then we're going to hard code that. Jump on over to my terminal. I'm running a 5-node network. Here you can see I've installed the dependencies. And then down here, I actually ran the deploy NFT and deploy run token to our local network. They gave us these 2 contract addresses, which, as I mentioned, I have hard-coded into this blockchain.js file. And now with my 1 single minute left, I'm going to jump on over to this game index.html. I'm going to go live. It's going to fire it up in my browser. So whenever I press, so you can see that the run score, I don't know if you can see it, but the run score is going to be incrementing. Whenever I jump up and hit an NFT, the NFT balance will increase. You can see the cumulative score increases anytime I run into an obstacle. And then now I want to connect my wallet. You can see I have my core wallet here, and I have 3.75 run tokens. Whenever I claim them, I can claim the NFT as well. It's taking a second for that to get approved. And then whenever I go to core, the balance will have increased, so 3.8. So there it is. Thank you guys so much. I know I'm literally down to the very minute. My name is Gabriel. You can check me out on Twitter here. You can go clone this repo later if you want to play along. I'm happy to answer any questions after I get off the stage. Thank you guys. Good.